Conway's Game of Life is a classic cellular automaton and zero-player game that we will be implementing today in Blender with geometry nodes to create this animation. The blend file is available through a link in the description, so check that out if you'd like, and let's get into it. Open Blender, delete everything except for the default cube, open up a geometry nodes window, and assign a new geometry nodes modifier. Conway's Game of Life is a simulation that exists on a grid, so we are going to create a grid geometry mesh primitive node as our first step. Then we'll pop in an integer input node and put those into the vertices x, y, and inputs of our grid node. That's going to determine how many subdivisions exist on the grid in the x and y directions. We're also going to add a value input node and pop that into the size x and y inputs of the grid node, which are going to control how big the actual geometry is in space. Then we're going to put both of those input nodes into a node group, which we're eventually going to name parameters, and that's so that we can just easily take this parameters node group and bring it to any part of our network, even if we're down in groups and subgroups, so that we can kind of have these global variables that can easily drive every part of our simulation if we want, or any part of our simulation I should say. So there we go. Name it parameters, and we'll come back to that later. We'll use it many other times in this setup. Conway's Game of Life works by determining whether or not each cell is alive or dead in each step of the simulation based off of 4 rules that are driven by the aliveness or deadness of the cells that neighbor each cell. So what we'll do in the repeat zone here is set the iterations to 9, which I do here, but then I think I press Ctrl Z and it goes back to 1, which later I'll see that the simulation isn't working correctly and figure out that the reason why is that the iterations are 1 instead of 9. But regardless, we're setting the iterations to 9 because we're going to cycle through all the different cells in the neighborhood of the current cell, starting with the offset of -1, -1, all the way to the offset of 1, 1, and everything in between, like -1, 0, -1, 1, etc. And then we'll sample the points at those positions on the grid geometry to get the actual index or the indices of each neighbor on the grid geometry, and then we'll store that in an attribute on the current point geometry that is named based off of the offset that corresponds to that neighbor index. So for example, the -1, -1 neighbor offset index will be stored in an attribute that is named as a string that is -1, -1. 1, 1 will be 1, 1, and everything else will follow the same rules. So here we're seeing the node setup to get the x and y offsets from the index that goes from 0 to 9. This works by taking a floored modulo and divide math node and then piping the index into the first input of each, and then setting the second value for each of these nodes to 3. You'll see here that the floored modulo node is set to the default 0.5, which is a mistake, and this is another reason why later on the simulation won't work correctly, in addition to having the iteration set to 1 instead of 9, so we'll fix that in the future. But the main idea here is that the floored modulo node will take the input, so 0 through 9, and whenever it gets over 3, it'll go back to 0. So you'll just, as it goes from, the index goes from 0 to 9, you'll get 0, 1, 2, and then 0, 1, 2, and then 0, 1, 2. And then the divide node divides it by 3, and then we're using this floor math node to take away any, we want it to be an integer, so we're taking any of the decimals or numbers after the decimal away. So then we'll end up getting 0, 0, 0, 1, 1, 1, 2, 2, 2. And so then we essentially have our indices, but or x and y offsets, but offset by 1. So then we'll subtract 1 from each. So instead of having 0, 0, 0, 1, 0, 2, etc., we'll have -1, -1, -1, 0, -1, 1, etc. And we'll get those x and y offsets that we talked about before. Then to get a mapping from these x and y offsets to the actual indices of the points on the grid geometry, what we'll do is we'll take the index of the current point and then we'll convert that to x, y coordinates, then we'll add that x and y offset that we've just calculated, and then we'll convert those xy coordinates back to an index, and we'll get the index of our neighbor. So here we can see we get the mapping between the index and xy coordinates by taking the index of the current point geometry and then the floored modulo with the grid resolution. So if the grid resolution is 32, then it's 0 to 31, and then when you hit 32 it goes back to 0. And so then the neighbors kind of wrap around, and the neighbor of the rightmost cells, or like the right neighbor of the rightmost cell, will be the leftmost neighbor of the grid. Same with top to bottom and bottom to top. And so then the floored modulo is all you need for actually the y offset. That's because the way I think about grids, I would actually switch x and y, and this is completely due to how the indices of the default grid geometry are set up in Blender, where you actually have the indices going starting at 0, 0 on the bottom leftmost point, and then the next index is actually 1 up in the y direction, so it goes up 0, 1, 2, 3, 4, etc., and then it wraps around, and sort of like, instead of going from bottom left to right and then up, it goes from bottom left up and then to the right, if that makes sense. So conceptually here, you're doing floored modulo with the y offset, and so you're adding that offset to the output of that floored modulo, and then x is going to only increment every grid resolution increment. So if grid resolution is 32, then as the index goes up, that x coordinate is going to remain 0 until from 0 to 31 until you get to 32, and then it goes up to 1, and etc. So then you go up another 32, and then you go up to 2, and then 3, and then 4. So that's why you divide the index by the grid resolution, take the floor, much like we did for the x, y, and offsets from 0 to 9. Then you're going to add the x offset to that output, and then we're going to convert back from the xy coordinates to an index. So now, after we've added the offsets, we're no longer at the xy coordinates of the current point, but we're at the xy coordinates of the neighbor defined by the x and y offset. So to convert back from xy coordinates to an actual index of a point on the grid, what we'll do is take the floored modulo of both the x and y coordinate components, and then we'll multiply the x component by the grid resolution, because when the x component is 1, the index is the grid resolution. So if the grid resolution is 32 and the y coordinate is 0, then the index is 32. And if x coordinate is 2, then it's 64, etc. And then you just add the floored modulo of the y component to that. So as you're just going up in the y direction, you're just adding, whatever it is, something between 0, if the y coordinate is 0, and all the way up to the grid resolution, depending on what you set that. So that's how you get the neighbor index. Just wrap that in a node group, and we can use that to set an attribute on our geometry that we can then easily pull to use in our simulation. So that's what we're doing here with the store named attribute node set to integer and point, and then we're going to create the name for that based off of the x and y offsets. So just convert both of those values to strings with a 0 as the decimal, and then join them with a comma delimiter, so it's just those two number strings separated by a comma. And then we actually only want to store this attribute if the offsets are not 0, 0, because that's just the current point. So this Boolean logic here checks to see if both of those offsets are equal to 0, and if they are both equal to 0, then instead we use a switch geometry node to just store the previous geometry instead of the geometry that's added the attribute. So we don't add an attribute for the 0, 0 neighbor, which is not actually a neighbor, it's just the current point. Moving on, we're just gonna pop all that into a store neighbor indices node group, and then we're going to pop in a simulation zone in which we are going to perform the actual game of life simulation. We'll start by initializing the state of each cell to be either alive or not alive with a Boolean attribute named alive. We'll initialize this randomly using a random value node set to Boolean type and the probability at 0.25. For the simulation, we're going to create a play the game of life node group that will determine the aliveness or deadness, basically whether or not that alive attribute is true or false for each step of the simulation for each cell. But before we implement that, we're going to want to instance a bunch of cubes on the points based off of the alive attribute. So if a cell or one of the points in the grid geometry is alive, we're going to instantiate a cube on it that is the size of a single cell size. And that's just the way that we're going to visualize it, and you'll see how that looks later on. So to make sure that the cubes are the correct size, we're going to have to calculate the cell size, and I'm going to actually add this to the parameters node group in order to do that. Because the cell size is going to be based off of the grid size and the grid resolution, I'm going to take those numbers out of the default group output fields and put them into their own nodes, their own value and integer nodes. And then what we're going to do is subtract 1 from the grid resolution and then do the grid size divided by the output of that subtract node. And then that's going to be our cell size output, which we will then use as the scale input to the instance on points node, which will scale the cubes to be that size. And we haven't actually hooked up the alive attribute to the selection input of the instance on points node, but we will do that later. So just pop all that into a node group, and then we'll actually go into implementing the rules of our game of life simulation. So first thing is we're going to set up this isNeighborAlive node group, which checks to see if a current neighbor is alive based off of the x and y offsets. We'll do this with a sample index node that samples the alive attribute, and then it'll use an index that comes from an integer attribute, which is going to use a name that is the input of the isNeighborAlive node group. And so that name will be something like we initialized before, like negative 1, negative 1, or 1, 1. And we'll just set all those manually, and then we'll get all the neighbors, and we're just going to do that 8 different times because I think that's a little bit faster than using a repeat zone. Not faster to set up, but faster to run within the simulation. Then we'll add all these up to get the total number of alive neighbors for the current cell. And the reason why we're doing this is because if you reference the rules of the game of life, you'll see all of them are based off of how many neighbors are alive or dead in relation to the current cell. So we'll pop all that into its own node group that is just the count living neighbors node group, and then we can use that as the basis for determining the state of each cell according to the rules of the game of life. So here we are setting everything up in a time lapse, and now I'll describe this setup once it's done. First rule is any live cell with fewer than 2 live neighbors dies as if by underpopulation. So if the living neighbor count is less than 2, then if that is not true, then you're gonna live, and if it is true, you're gonna die. And so then we go on to rule number 2, which is any live cell with 2 or 3 live neighbors lives onto the next generation. So if that is true, so if the living neighbor count is equal to 2 or it's equal to 3, then if that's true, then the living neighbor is going to switch, the aliveness of the current cell is going to live. It's going to switch to true. If it's false, it'll switch to the output of rule 1. And then rule number 3, any live cell with more than 3 neighbors dies as if by overpopulation. So if the living neighbor count is greater than 3, then, if that's true, then alive, the output, which is going to get set to the alive Boolean attribute, is going to be set to false. And if the output of rule number 3 is false, then we're going to revert back to rule number 2 or rule number 1, depending on the output of rule number 2. And then rule number 4 is any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. So this is actually a dead cell. So if we're assuming all the other rules 1 through 3 apply to living cells, but rule number 4 is the only one that applies to dead cells. So we'll have this switch node with the alive attribute as an input to the switch input. And so if the current cell is not alive, so false, you'll revert to rule number 4, which is if the living neighbor count is equal to 3, then that dead cell will become a living cell. And so we wrap that in a node group, which is determine alive, and then we store that as the alive Boolean attribute on the current cell. So as I mentioned before, we actually need to set the alive attribute to the selection input of the instance on points node. So here I was wondering why are all these cubes present, and I had forgotten to set this up. So I just set that named attribute node there, input it, and we can see that these randomly selected and initialized to be alive cells are visible. And then we can try running the game of life, but nothing's working, and I'm again confused, and this is related to the initialization of the neighbors. And so we need to make those 2 changes where we change the iterations to 9 and we change the floor modulo second value to 3, and then we actually have a working game of life simulation. So the next effect that we're going to add is this geometric trail effect, where the simulation moves down by the cell size every frame, and you just see the sort of like crystallized form of the simulation go down in the z direction every frame. So what we're going to do is use a set position node with an offset with a vector with just a z component that is the negative cell size, and then we're going to join that with the previous geometry. But then if you're doing that, you're copying a bunch of geometry every frame, which doesn't work. So at first I was going to use this like skip variable and then delete that geometry to not copy redundant geometry, but I realized a better way was just to use a separate geometry channel within the simulation loop, and then just set that position, and then join the simulated geometry with that other geometry channel each frame. I set this to join both those geometry streams that are present in the simulation loop after the simulation loop, which doesn't quite work because then you're duplicating the simulation geometry and you'll get weird z-fighting in the render. What I end up doing to fix this is I just add the set position node after the join geometry node that's within the simulation loop, but also it would probably work just to use the second geometry stream as the output. So, you know, there's a million ways to solve a problem. Choose the one you like the best, but that's the way it's set up here. Next, we're going to add a delete geometry node to delete any points that are below a certain z position in the simulation, because we just don't need them because they're not visible below a certain point, and the less geometry, the faster things will run, so that's why that's there. After some cleanup and some naming of inputs and outputs to the simulation group, we're going to add a transform geometry node and just rotate the entire geometry by a little bit around the z-axis every single frame. So we'll use that frame input and then multiply that by a pretty low number, pipe that into the z component of a combine xyz node, and pipe that vector output into the rotation input of the transform geometry node. And now we've got this rotating, animating, game of life simulation, 4-dimensional, sort of whatever you want. And what we want to do now is pop in a set material node and then edit materials and lighting and get everything ready for our final render. So we're going to pop into that shader editor, user principled BSDF, ramp up the subsurface, change the colors to this bluey type green type color scheme. We're going to change the size of everything. At a certain point, we'll change the size of the instances to not be exactly the cell size, but actually a little bit smaller than that. I think like 0.7 or 0.6. I can't remember exactly what I landed on, but you'll see it on the screen right now. I started in Eevee, eventually switched back to cycles, which is something that we all know and love, or at least I know and I love. And I'm using the position of the instances, the Z components, to change the color so they get more blue as they go down, and the very top instances are all white. And then I set this deep or intense depth of field and render out our final animation. I hope you enjoyed this tutorial. I hope you learned something, and above all, I hope you had fun. Until next time.